So in this section, we're going to look at what is called conditional probability. And so the idea behind conditional probability is that there is an event that happens that's like a condition that has to first be met. And then after that event happens, you then want to see how likely it is that another event will happen after the fact. So up to now, we've basically just been doing individual events by themselves, and there's been varying degrees of complexity as to the conditions for what it means to be successful. Here, we're stepping things up a notch and looking at multiple possible events, one after the other. So we're interested in seeing the probability that an event E is going to occur, and then we have some sort of partial knowledge about the results. And so we then have to adjust the probability of E based on what's already happened. So for instance, if I draw a card from a deck of cards and I ask you the probability that it is a spade, you would say 1 out of 4, because there are 4 different suits, all equally divided. So there's a 1 in 4 chance that it's a spade as opposed to a heart, diamond, or club. If I were to draw a card from a deck and then tell you that it was black, then that changes the probability, because there is a condition, a prior condition that is met, and now that I know the card is black, in fact, there's only a 1/2 chance that it is a spade. Because if I know it's black, either it's a club or it's a spade. And so there's a 1 out of 2 chance that it meets the condition that I'm looking for based on a prior condition that it is black. So this is known as conditional probability. So the way this is read here, this is the probability of E given F. Here it is kind of written out in words. The prior condition is underneath the denominator of a fraction here. And you'll notice you've got like this line, and so it's the one that's behind it. So, you know, if you were writing a fraction kind of sideways, like 1 out of 2, this would be something like 1 out of 2 here, where the probability of that is the denominator there. What is on top is what we've seen previously, the probability of E intersecting F, or the probability of E and F. So the two events happening together divided by the probability of the prior condition. That is the formula for conditional probability. So here they say, find the probability of A and B. And you notice what they give us. They give us the probability of A, they give us the probability of B, and they give us the probability of A or B. Let's recall a formula that we saw previously, which was the probability of A or B. That is equivalent to, that went a little crazy there, that is equivalent to the probability of A plus the probability of B plus, or I'm sorry, minus the probability of A and B. So using this formula, we can then say, all right, if I want to find the probability of A and B, I know A or B. I know the probability of A. I will add the probability of B, and then subtract whatever the probability of A and B is. We'll write it with this symbol just because it's faster. So we'll do a little bit of algebra here. So 0.3 plus 0.48 is 0.78. So 0.66 equals 0.78 minus the probability of A intersect B. So then what we're going to do is we're going to subtract 0.78 from both sides here. So 0.66 minus 0.78 is negative 0.12. That equals negative probability of A intersect B. So then that basically just means that A and B is equivalent to 0.12. You divide by -1 on both sides to get rid of the negative. And so the probability of A intersect B, or A and B, is equivalent to 0.12. So there's a 12% chance that both events happen at the same time. So now we want to find the probability of A given B. We just saw the formula for that. The probability of A given B. So since the B is the given, the value for the probability of B is what's going to go in the denominator. So this is going to be 0.48 because that is the probability of B. And actually, I'm getting ahead of myself here. Let's write the formula first. So this is probability A and B. And then this will be divided by the probability of B. So as I mentioned, the probability of B, we already know what that is. That is 0.48. We just found the probability of A and B. That is 0.12. So then if you do 0.12 divided by 0.48, you will obtain 0.25. In a school, we've got 30% in sports, 45% in clubs, 12% are in both. And so then we select a student at random. What's the probability that they are in sports? Well, so the probability of sports, they go ahead and tell us that. That's 45, or let's see, that's 30%. What's the probability they participate in clubs? Well, they tell us the probability of clubs. That is 45%. Then they say, given the student participates in clubs, was the probability they participate in sports? So what this means, given clubs, so this is going to be probability of sports given clubs. So clubs is what we know beforehand. Well, how would we find this? This is the probability of sports and clubs together divided by the probability of clubs. And probably what will be better is if we do the decimal versions of these. This is 0.3, this is 0.45. So sports and clubs, that's 12%. 12% is another way of saying 0.12, 0.12. And then the probability of clubs, we found that before, that's 0.45. So if we do 0.12 and divide it by 0.45, that gives us 0.27. If we round it off, it's 0.26 repeating. So we'll round that off as 0.27, or that's roughly 27%. Given the student participates in sports, so given sports, what's the probability that they participate in academic clubs? So here we're going to have our same formula, but it's going to be in reverse. The probability of club given a sport. What is that going to be? Well, from the formula, we know that this is going to be the probability of sports and clubs, the probability of the two of them together, divided by the probability of whatever's given. So divided by the probability of sports. As before, we know what the probability of the two together is. That's 0.12. You're going to divide that by the probability of sports. The probability of sports is 0.3. So then let's see what 0.12 divided by 0.3 is. That is equal to 0.4. If you're going to make that a decimal, please recall the fact that this is equivalent to 0.40. So as a percentage, please recall this is 40% and not 4%. Those are two very, 4% is 0.04 for those keeping track. Okay, here's another one. We've got a group of employees and we've got their job function. We've got the laborers, the middle management, and the upper management. And then we've got the education levels. So we've got no high school, and college degree. Let's find the total values for each of these. So if I add down here, 54 plus 138 plus 26, that is going to give me 218 laborers. Then for the middle management, we're going to have 8 plus 46 plus 28. If we add those up, we get 82. And then for upper management, 0 plus 3 plus 17, that is 20. Go the other way, 54 plus 8 plus 0, that is 62. Here we've got 138 plus 46 plus 3, that is 187. And then we've got, for this last one, 26 plus 28 plus 17. And that is 71. And then if all goes well, if I add these numbers, that should give me the same amount as these numbers, both of which should add up to 320 if all goes well. And it's not a bad idea to check that real quick here. So that is, adding down is indeed 320. Adding across, that is also 320. All right. So the grand total of people is 320. So what's the probability that someone is a laborer? So there's no real restrictions to the conditions here. As long as the person's a laborer, there are 218 of them. The grand total is 320. So the probability for being a laborer is going to be 218 out of 320. And if we divide that, we get a decimal of 0.68 approximately. We'll do the squiggly one since it's approximate. Is that 0.68? So there's roughly a 68% chance that if you randomly pick an employee, they will be a laborer. What's the chances we pick someone in middle management? All right, people in middle management, 82, still out of 320 total. All right, so let's see what that is. So we've got 82 out of 320. Let's find out what that is. So we've got 82 divided by 320. That is 0.26 if you round it off. So again, it is approximately 26%, give or take. What's the probability that someone has only completed high school? So completed high school only, that's this group, 187 of them out of the total of 320 employees. So for this one, we're going to do 187 out of 320. So let's see what 187 out of 320 is. That is 0.58 approximately. So about a 58% chance. And lastly, for this slide, we've got what's the chances of someone getting having a college degree. So the people with college degrees is 71. And again, we're still looking at out of the total population of 320. So if we do 71 out of 320, 71 out of 320 is approximately 0.22. So that is roughly 22%. So again, these are all relative to the entire population of the entire factory here. So now we're going to step things up a notch. What is the probability that someone is a laborer given that they do not have a high school diploma? So the probability, so they do not have a high school diploma. That means we are limiting our world to this line only. What's the probability that someone is a laborer given they do not have a high school diploma? So there are 54 people who meet that description out of 62 total based on that condition. So because we're limiting our view to only those who do not have a high school diploma, that means that this probability is going to be 54 out of 62. And if we work out what 54 divided by 62 is, that is approximately 0.87. So if you pick someone, if you know an employee does not have a high school diploma, there is an 87% chance that they are a laborer. So it's very likely that if you know the person doesn't have a diploma, they are going to be a laborer. Now, let's look at a slightly different scenario. What's the probability that someone does not have a high school diploma given they are a laborer? So if it's given they're a laborer, now we are looking at this. We are only looking at the laborer column. And so it's given that the person's a laborer. What's the chance that they do not have a diploma? Well, that's 54 don't have a diploma out of 218 laborers. So this one is 54 out of 218. So let's see what that is. 54 divided by 218. That is approximately 0.25 if you round it off. So your assumptions make a big difference in the outcome. If you assume or if you know that the person doesn't have a high school diploma, it's very likely that you will pick someone who is a laborer. If you know someone is a laborer, though, that does not necessarily guarantee that they do not have a high school diploma. There are quite a few other laborers who do have either high school or college degrees. So then moving on to the next bit here. What's the probability that someone's in upper management given they have a college degree? All right, so let's start with our given. Our given is college degree, which is this group right here. So there are 71 people who meet that condition. The people in upper management, there are 17 of them. So this is 17 out of just those 71. That is the entirety of our world. Everything else is irrelevant to us. We're only interested in those with a college degree. Of those with a college degree, 17 out of those 71 people are in upper management. Let's find out what 17 out of 71 is. That is 0.24. So roughly a 24% chance that a person meets that description. On the flip side, what's the chance that someone has a college degree given they're in upper management? So what's our given this time? This time our given is upper management. So there are only 20 people in upper management. And of those, 17 of them have a college degree. So we're still talking about the same 17 people, but this time our frame of reference is the 20 individuals in upper management. And 17 divided by 20 is 0.85. So if you know someone is in upper management, there's an 85% chance that that is someone with a college degree. So if you're in upper management, there's a good chance you have a college degree. However, just because you have a college degree does not guarantee that you have found your way into upper management. Ain't that the truth? All right, so here's another example that's kind of along similar lines. So this time we've got vaccine testing. This is this example was written some time ago, but it's eerily appropriate for the world in which we now live. All right, so we've got 3 different possible treatments here for a disease, and we're basically charting whether or not the patient's condition improved, didn't change at all, or if it actually got worse. Let's find the totals for each of these rows here. So 26 plus 7 plus 2. This is going to give us a total of 35 patients who improved in some way. Those who saw no change, we've got 11 plus 28 plus 23. That will give us a grand total of 62 who didn't change in any fashion. And then for those who actually got worse, we've got 3, 5, and 15, which is a grand total of 23. All right, so let's check this out. What's the probability that a person's condition improved? And we do know going in that there are 40 patients in total. So the grand total of people who saw improvement is 35 out of 40. So spread across all 3 of these possible treatments, those odds are actually going to be pretty good. What is 35 divided by 40? That is 0.875, exactly. I don't even have to round it off. 0.875. Okay. What's the probability that a person's condition did not change? So the total for no change is 62. And again, this is out of a grand total. Let's see. Oh, hang on a second. Hang on. It's 40. Okay, it's actually 120. We need to back up here a second. Because it's 40 for each group, but then that actually means that there are 120 patients altogether. I grew suspicious when the number of patients who had no change actually exceeded the total number of patients who were tested in the first place. That's kind of a cause for concern. Let's try this again. 35 divided by 120 is actually 0.29 approximately. Switch over from the eraser. 0.29. People who did not change, that's going to be 62 divided by 120, which is 0.52 approximately. So more than half of the patients experienced no change whatsoever. And then what's the probability that a person's condition worsened? Well, the number of people who their symptoms got worse, that's 23. And again, there's a grand total of 120 patients who fit that description. 23 divided by 120 is approximately 0.19. So roughly 19% of patients got worse. What is the probability that a patient's condition did not improve? Okay, well, that's basically going to be the no change and the worsen put together. We could add the individual numbers. We could also just add the probabilities directly. If you add 0.52 plus 0.19, then that will give you a grand total of 0.71. And fun fact, that is also the complement of 0.29. If you do 1 or 100% minus 29 or 29%, you will also get 71 or 0.71 for that. So that's a good sign. All right, so what is the probability that a person's condition improved given they got treatment A? So the given is treatment A. All right, so treatment A, let's see, they told us it's 40 for each of them. So there's 40 there, 40 there, 40 there. Each treatment has a total of 40. So improvement is 26 of those 40. Let's find out what 26 divided by 40 gives us. That is 0.65, so there's a 65% chance the patient got better if they got treatment A. That's a good sign. The person received treatment A given their condition improved. So if they improved, now we're talking about this. So of those 35 individuals who we know improved, of those 35, 26 of them got treatment A. So you notice 26 is still the numerator here, but we're changing our frame of reference to the 35 people who got that particular treatment, treatment A. 26 divided by 35, that is 0.74. And again, that's approximately. So there's about a 74% chance that you will. If you know someone improved, there's a 74% chance that they had treatment A. So we want the probability that a person's condition worsened given that they got treatment C. So the given is treatment C. Again, all of these treatments have 40 patients, so the frame of reference is going to be 40. Of those who got worse from that group, 15 of them, 15 got worse out of treatment C. 15 divided by 40 is going to be 0.375 or 37.5%. This one, given that their condition worsened, so given that it's worse, which is this group, what's the probability they got treatment C? Well, out of a total of 23 who got worse, what that means is that 15 of those 23 got treatment C. And if we find out what 15 divided by 23 is, that is not going to be a good percentage. It's about 65%. So I suppose that's not terrible, but that's not exactly good either. Treatment C seems to be doing more harm than good. All right, so here we've got our conditional probability formula. And so now we have kind of a general multiplication rule. So the probability of E and F is equivalent to the probability of E given F times the probability of F. So this is basically just an algebraic rearrangement. You multiply by P of E on both sides, and it gives you a new formula. Here's what the formula looks like if you switch E and F around. They mean the same thing. The probability of them together equals the probability of the first given the second times the probability of the second. So that's the general multiplication rule. Let's see this in action, shall we? Assume that 2 cards are drawn from a 52-card deck without replacement. That is a very key assumption here. We are not replacing the cards after we draw them. What's the probability that both cards are aces? So if I draw an ace from the deck the first time around, well, when I go in for my first pick, There are 4 possible aces I could choose. There are a grand total of 52 cards to pick from. Then I'm going to multiply for the next event that comes after that. I have taken an ace out of the deck. There are now only 3 aces left. That's what it means when we say without replacement. I have not replaced the ace of diamonds. I draw the ace of diamonds. I keep it. I don't put it back in the deck. There are 3 aces left, and in the total deck, I'm now down to only 51 cards because I have removed one of them, so there's 1 fewer card in the deck. If we multiply, 4 times 3 is 12, 52 times 51 is 2652. We could then reduce this or divide it, so 12 divided by 2652 is 0.0045, which is basically a 0.45% chance of that happening. So it's not very likely to get a pair of aces, for instance. A box contains 3 green marbles, 5 green marbles, 3 blue marbles, and 7 red marbles. 3 marbles are selected at random from the box, 1 at a time. And again, the key words here, without replacement. Find this probability. So find the probability. The first one is green, the second one's blue, and the third one is red. For those keeping track, 5 plus 3 plus 7 gives me a grand total of 15 marbles at the very beginning. So what's the probability that I pick a green? Well, there are 5 greens to start with out of 15 to pick from for event number 1. Now I'm interested in the second one being blue. Well, there are still 3 blues because I took out a green, but all 3 blues are still there. Since I've removed 1 green marble, that means I'm down to 14 total of the possible marbles. From here, I can then say, all right, now I want the third one to be red. Well, all 7 reds are still there. I'm holding on to a green, I'm holding on to a blue. There's 2 that I'm holding on to. 13 are left that are possible to pick from. Multiply across the top. 5 times 3 times 7 is 105. 15 times 14 times 13 is 2730. And then you can say, hey, calculator, what is 105 divided by 2730? And the calculator would be like 0.038. So that's roughly a 4% chance that will happen. What are the probabilities that the marbles are all different colors? All right, let's think about this. So if they're going to be different colors, you could have what just happened. You could have green, blue, red. That's one possibility. You could also keep the green one first, but then switch around and do green, red, blue. That would be another one. You could then have the choices of blue coming first. So you could have a blue, a green, and a red. Or you could have a blue, a red, and a green. There's 2 different ways the blue could be first. And then lastly, you could have the chances of red being first. You could have red, green, blue, and then red, blue, green, something like that. So altogether, there are 6 ways that can happen. Now, it turns out with the fractions and multiplying, you're still going to get this same fraction or this same decimal, 0.038. However, this time around, there are now 6 different ways you can mix and match, getting all different colors. So then what that means is I'm going to do 6 and multiply it by the 0.038 that I just obtained, because that's the probability for one combination of mixing and matching these. If I do all 6 of those, it's now up to a 0.231 as the probability for having all the colors being different. Not necessarily green, blue, red, but one green, one blue, one red in some order. Let's look at another one here. The first marble is red, the second marble is blue, and the last marble is not green. All right, so let's look at this first event. Chances of drawing a red. I have 7 reds to start with, and at the very beginning, there are 15 to pick from. Okay, next I want the chances of drawing a blue. There are 3 blues. I drew a red, so none of the blues have been touched yet. Since I've removed 1 red, there are 14 of these to go that are left. And then lastly, what's the chance of not getting a green? Well, I'm down to a total of 13 marbles. I've taken away one of these, I've taken away one of those, so there's 2 left from this group and 6 left from that group, which is a grand total of 8. Another way is you could say 13, all 5 of those are there, which means 8 are left because you do 13 minus 5. However you figure it out, there are 8 marbles that are left the very last time I picked, because instead of 3 blues, now I have 2. Instead of 7 reds, now I have 6. So the 2 of them together is 10. I've taken 1 from each. That takes me down to 8. Let's see. 7 times 3 times 8 is 168. The bottom number is going to be the same still, 2730. That will not have changed since the last time we did that. So 168 divided by 2730 is 0.062 if you round it off. So that is that probability. Next part, this is the same scenario here. We're drawing 3 one at a time without replacement. What are the probability that all the marbles are red? Well, let's see. First draw, 7 out of 15 is the chances of drawing a red marble. One of the marbles is gone, so 7 is now down to 6. One of the marbles is gone, so 15 is down to 14. Let me do this all over again. There are 2 marbles are gone now, so there are 5 reds left to choose from. 2 marbles are gone that are both red. There are 13 left to choose from. Seven times 6 times 5 is 210. We're going to divide that by 2730 again. Let's see what that gives us. That is 0.077 if you round it off. So about an 8% chance, roughly. What's the chances that none of the marbles are red? Well, let's see. So for the first event, there are 8 non-reds. There's 5 greens and 3 blues. There are 8 that are not red for the first event out of 15. For the second event, there will be 7 left that are not red out of 14. And for the third event, there will now be 6 left that are not red out of 13. 8 times 7 times 6 is 336 out of 2730. That is 0.123, or 12.3%. And then what are the chances that all the marbles are the same color? Well, we already know all red. We already have red, red, red. That is 0.077. Let's figure out what blue, blue, blue is. So for blues, there's 3 for the first draw out of 15 times 2 for the second draw out of 14 times 1 for the last draw out of 13. That's going to give you 6 out of 2730. Let's figure out what 6 out of 2730 is. That is 0.0022. And then last but not least, for 3 greens, there's 5 for the first pick out of 15. There is 4 for the second pick out of 14. And there is 3 for the last pick out of 13. That's going to give you 60 out of 2730. Which is 0.022. That's for green, green, green. If you add all of those up, 0.077 plus 0.0022 plus 0.022, you will get approximately 0.1012, which is roughly a 10% chance that all of the marbles you pick will be the same color, regardless of what color you're trying to get. Two events are independent if the previous event has no impact on the probability of a later event. So for independent events, these are 3 different ways of saying the same thing. If E given F is the same as probability of E, they are independent. If F given E is the same as probability of F, they are independent. If the probability of E and F is equivalent to the probability of E times the probability of F, those are independent. Those are 3 variations that say the same thing. And so this is the situation where prior results, the condition, really does not matter. All right, so we've seen this kind of thing before. We've got to find A or B, B or C, A or C. So again, just to recap, definitely want to know this formula for the test. Let's maybe use E and F. So the probability of E or F, that is going to be equivalent to the probability of E plus the probability of F minus the probability of E and F. That is definitely a formula you will want to know come exam time. So find the probability of A or B, all right? So probability of A or B, we're going to take the probability of A, which is 0.45. We're going to add the probability of B, which is 0.6. And then we will subtract the chance that both of them happen together. That's 0.27. And let's see what that is. 0.45 plus 0.6 minus 0.27 is 0.78. Okay. B or C? Well, we have the probability of B, that is 0.6. We're going to add the probability of C, which is 0.55. And then we're going to subtract B and C, which is 0.42. So 0.6 plus 0.55 minus 0.42. That is 0.73. And then finish out this slide here, probability of A or C. So the probability of A, that's 0.45. Add the probability of C, that is 0.55. And then subtract A and C, that's 0.35. So 0.45 plus 0.55 minus 0.35 is 0.65. So that's just kind of a rehash of a formula that we have seen before, but it's good to review it because it is an important formula. So now we are going to be checking for independence. The probability of B given A. So if we look back earlier here, so E and F is E given F times probability of F. That's the formula that we need. So we're going to say probability of E and F and actually we probably just want to do this. So we'll say probability of E and F divided by probability of F. That is how you would find probability of E given F. The thing that's given is what you're dividing by. So here we've got probability of B given A. So this is going to be the probability of B and A. That's going to be 0.27. So you do A and B together, which is probability of A and B, and we divide it by the probability of A. So that's 0.45. Let's see what 0.27 divided by 0.45 is. That is 0.6. Next, probability of B given C. So we need to do B and C together, which is this one, 0.42. That needs to get divided by the probability of C. So the probability of C is 0.55. So what is 0.42 divided by 0.55? That is 0.76. And for this last one, probability of A given C, well, if you do A and C together, that's 0.35. You will divide that by the probability of C. The probability of C is 0.55. So 0.35 divided by 0.55 is 0.64 if you round it off. So then they say, determine if any of those are independent. Well, if something is independent, that means that probability of E given F so the probability of E given F just equals the probability of E. So in this case, something interesting happened up here. So the probability of B given A actually turns out to be the same as the probability of B, because what you'll notice is that here is the probability of B, 0.6. Here is the probability of B given A. So A and B are independent. That is how you would use the definition of independent events. So A and B are independent. The other ones don't match. 0.76 doesn't match any of those. 0.64 does not match any of those. So that is the end of section 4 and conditional probability.